The next exercise in your book has an example of a three-phase factory unit that needs to have the number of final sub-circuits allocated to it. Our primary reference will be table C9 for this one. Same as in the previous task, we'll be establishing the correct number of circuit breakers for final sub-circuits for this particular installation. Let's begin with the lights. This installation contains 10 high bay mercury vapour lights. They'll be on a 16 amp circuit breaker. If each light draws 1.85 amps, that's the value we need to allocate when we're working out the load. Previously, table C9 would have advised us that a value of 0.5 amps would be sufficient. That's clearly not the case here. We've been given our value of 1.85. Putting all 10 on these is going to exceed our value of the circuit breaker. So a common sense approach to this would be to halve the number on each circuit. I'm going to place 5 lights on each circuit. Next, we'll continue on with the double 10 amp socket outlets. Table C9 will be our next reference. A quick look at table C9, and we know that we've been allocated a 20 amp circuit breaker. We'll assume a 2.5mm conductor, as that is the minimum size for a socket outlet. And we'll come across to the table and look for the appropriate column to see which one interests us. 10 amp socket outlets are broken up into non-domestic and domestic. The non-domestic one, and this being a factory, this is the one we're interested in, doesn't mention or not mention permanent air conditioning, so I'll suggest that we'll go with the column without permanent air conditioning. And what we see is the allocation of each point is worth 2 amps. Further up the top, when we have a look at the 10 amp socket outlets, we see there's reference to footnotes 3, 7, 8 and 9. Let's check those. Of particular interest to us, footnote 3, which simply put says that for a double outlet we need to consider that to be worth 2 points. For a triple outlet, be worth 3 points, etc, etc. So now our 12 doubles has actually turned into 24 points. Because we've got 12 doubles, which turns into 24 points, and each one of those being worth 2 amps each, we now have our 24 points multiplied by 2, which gives us 48. Those 48 amps need to be broken up across 20 amp breakers. That's going to give us over 2 and therefore 3 circuits. For convenience, seeing our 12 doubles can be broken up into 3 evenly, I've decided to go that way, and I've allocated 3 power circuits. When I evenly break up that load, I end up with a total of 8 points on each one. Let's move on to the 3-phase 32 amp socket outlets. Each one of these is going to be supplied by a 32 amp breaker. Again, you recall clause C5(1) that says that each item of equipment that has a current rating in excess of 20 amps per phase should be connected to a separate and distinct circuit. Therefore, each of the 32 amp 3-phase socket outlets supplied by the 32 amp circuit breaker will go on their own circuit. 1 point on each. That now gives us a total of 8 circuits, some being single phase and some being 3-phase.